Imagine you wake up at 0400 inside a steel compartment roughly the size of a walk-in closet, sharing that space with 5 other people, somewhere in the middle of the Pacific Ocean, with the nearest grocery store approximately 900 miles away, and you will not see land for another 63 days. Now scale that single compartment up. There are roughly 5,000 people living inside this vessel, all of them awake in rotating shifts. All of them burning calories at rates that civilian desk workers never approach, all of them consuming 3 full meals per day plus a midnight ration called the mid-rats, and not one of them can place a delivery order. Not one of them can walk to a vending machine that connects to the outside world, and not one of them has the option of skipping the system entirely if it fails. The USS Gerald R. Ford, the most advanced aircraft carrier ever commissioned by the United States Navy, is not primarily a weapons platform. It is a city. It is a sealed, floating, blackout-capable city that must feed itself completely from within. And the question that nobody outside of naval logistics ever stops to ask is this: how does 5,000 pounds of food move from a refrigerated hold deep inside a nuclear-powered warship to a human hand holding a tray every single day on schedule without failure? Ones in conditions that would shut down every civilian supply chain on Earth within 48 hours? The answer is not intuitive, and it does not begin where most people assume it begins. It begins months before the ship ever leaves port, inside a procurement and inventory architecture so precise that a single miscalculation in caloric planning does not merely mean someone goes hungry. It means operational readiness degrades. Cognitive performance declines across 5,000 people simultaneously, and the commanding officer of a $10 billion nuclear vessel begins managing a morale crisis in hostile waters with no resupply option on the calendar. This is where civilian logic about food distribution collapses entirely, because in the civilian world, supply chains are designed around the assumption of replenishment. A grocery store does not need to carry 60 days of inventory because a truck will arrive tomorrow. A restaurant does not need to forecast protein consumption for 5,000 people across 2 months because the market is open in the morning. The Ford operates under the opposite assumption. Every calorie that will be consumed during a deployment must either already be on the ship or arrive via a process so complex and weather-dependent that it cannot be treated as reliable. The baseline load for a standard deployment is staggering in its physical dimension. The Ford carries approximately 1 million pounds of food at the start of a full deployment cycle. That is not a metaphor. That is a literal measurement of stored biological fuel distributed across refrigerated spaces, dry goods storage compartments, and freezer holds that are integrated directly into the ship's structural design, not added as an afterthought, but engineered into the hull as a primary survival system on equal standing with propulsion and armament. The refrigeration infrastructure alone draws on power systems that would be recognizable to a mid-sized commercial cold storage facility, except that this facility moves at 30+ knots, rolls with ocean swells, absorbs vibration from 2 nuclear reactors, and must continue operating without an external power grid, without a repair technician arriving from outside, and without the option of temporarily shutting down because the vegetables will not wait. Here is what most people never consider. The thermal management of food storage on a carrier is not a passive system. It is an actively monitored, continuously adjusted thermal architecture where a sensor failure in a single freezer compartment can trigger a cascade that threatens weeks of protein stores. And the people managing that system are not professional refrigeration engineers hired from the civilian sector. They are enlisted personnel in their early 20s who have been trained with a precision that exceeds what most civilian food safety inspectors will ever achieve, because the consequence of their failure is not a health code violation. It is 5,000 people losing access to stored protein in the middle of an ocean with no alternative. But storage is only the first constraint. The more invisible and more psychologically consequential system is the movement of food through the ship itself, and this is where the Ford's architecture creates problems that have no civilian equivalent. The ship has 25 decks. The galleys, the primary food service facilities where meals are actually prepared and served, are not located adjacent to the storage holds. They cannot be, because the storage holds must be positioned for weight distribution, structural integrity, and damage control logic that has nothing to do with kitchen convenience. This means that food moves vertically and horizontally through a vessel that is constantly in motion, through passageways designed for naval operations rather than logistics flow, carried by personnel who are simultaneously responsible for other duties, and using elevator systems and manual handling techniques that must account for the fact that a ship in heavy seas creates dynamic load conditions that can turn a 200-pound cart of provisions into a projectile. The supply department aboard the Ford is not a background function. It is one of the largest departments on the ship, and the chief culinary specialists who run the food service operation manage what is functionally a multi-unit restaurant chain, serving 5,000 covers per meal period. Except that their kitchen equipment cannot be replaced from a supplier. Their staff rotates on watch schedules that have nothing to do with kitchen staffing logic. And their menu must balance nutritional requirements calculated by naval dietitians against the psychological reality that food is one of the most powerful tools available for maintaining morale in a sealed environment where the absence of variety becomes a form of psychological pressure that accumulates invisibly over weeks. This is where the system intersects with behavioral psychology in ways that naval planners have understood for generations. Food is not merely fuel on a warship. It is one of the primary mechanisms through which command maintains psychological stability across 5,000 people who are living in close quarters under operational stress in a sensory environment defined by steel, noise, artificial light, and the complete absence of the ambient stimulation that civilian brains depend on for emotional regulation. When the food system degrades, the first failure is not nutritional, it is motivational. Cognitive performance begins to decline not primarily from caloric deficit, but from the psychological signal that the environment is no longer under control. And in a system where every person's performance directly affects the operational readiness of a nuclear-capable vessel, that signal cannot be allowed to propagate. This is why the menu planning cycle on a carrier is not a simple nutritional calculation. It is a behavioral management tool. The cycle runs on a rotating schedule long enough to prevent menu fatigue, with deliberate variation engineered across cultural preferences represented in the crew, with special meal events including holiday meals and steel beach picnics used as temporal anchors that give crews a sense of forward momentum through what would otherwise be an undifferentiated stretch of days. If you lived aboard the Ford for 90 days, with no variation in the food system, no special events, and no acknowledgement of time passing through the one ritual that crosses every cultural line in human experience, the shared meal, the psychological consequences would become operationally measurable within weeks. The Navy knows this because it has studied it, and the food distribution system is engineered around the finding. But here is where the pressure intensifies, because everything described so far assumes that the ship is operating normally, that the storage systems are functioning, that the supply department has its full complement of trained personnel, that the electrical systems powering the refrigeration are stable, and that the ship is not in a situation where damage control, medical emergencies, or operational tempo have pulled personnel away from food service duties. The Ford is designed to operate in precisely the conditions where all of those assumptions fail simultaneously and the food system must continue. The redundancy architecture built into the ship's food distribution capability reflects this requirement. There are backup power feeds for refrigeration systems. There are emergency ration stockpiles staged at points throughout the ship that are separate from the primary galley system, designed to sustain the crew through a period when the main food service infrastructure cannot function. There are procedures for field expedient meal preparation that bypass the primary kitchen equipment. None of these backup systems are comfortable. None of them are designed for extended use. They are designed to sustain 5,000 people through a crisis window long enough for the primary system to be restored, and the personnel training around those backup systems is conducted with the same seriousness as combat system training. Because in the Navy's operational calculus, a crew that cannot be fed is a crew that cannot fight. And a crew that cannot fight is a mission failure regardless of how many aircraft are on the flight deck. The resupply mechanism that extends this system beyond the initial load is called a vertical replenishment or underway replenishment, and it represents one of the most choreographed logistics operations in the modern military. When the Ford requires resupply at sea, a combat logistics force vessel pulls alongside at a fixed distance while both ships maintain speed and course in open ocean, and cargo is transferred via highline systems while helicopters simultaneously conduct vertical lift operations overhead, moving palletized food stores from the supply ship to the carrier's deck in a continuous flow that must be completed within a window defined by weather, threat environment, and operational schedule. The precision required for this operation is not incidental. A failure in the transfer rig does not mean a delayed delivery. In certain sea states, it means personnel in the water. The food that arrives via this process must then be immediately integrated into the ship's inventory management system, routed to the appropriate storage spaces, logged against consumption projections, and accounted for in the running caloric budget that the supply officer uses to manage the remaining deployment. This inventory management system is not a spreadsheet. It is a purpose-built naval logistics architecture that tracks thousands of line items across multiple storage locations, interfaces with the menu planning system, generates consumption projections based on crew size and operational tempo, and flags shortfalls far enough in advance that the commanding officer can request resupply before a critical threshold is reached rather than after. If this system fails, if the data becomes corrupted, if the tracking falls out of synchronization with physical inventory, if consumption projections are built on faulty assumptions, the first visible consequence is not immediate hunger. It is a miscalculation that becomes apparent 3 weeks later when a storage compartment that was supposed to contain 30 days of protein contains 12, and the next replenishment window is 21 days out. And the commanding officer must now manage a gap with no good options and 5,000 people who will notice the change in their meals within 48 hours. This is not a hypothetical scenario built for dramatic effect. It is the category of failure that naval logistics training is specifically designed to prevent because the consequences propagate in ways that are disproportionate to the initial error. What begins as an inventory discrepancy becomes a menu degradation, which becomes a morale signal, which becomes a performance variable across every department on the ship, which ultimately becomes a question of whether the vessel can execute its mission at the operational standard required. The food system is not peripheral to the ship's warfighting capability. It is structurally integrated with it in ways that are invisible when the system works and catastrophic when it doesn't. And the people who keep it working are not celebrated in the public narrative about carrier aviation because their success is measured in the absence of failure rather than the presence of dramatic achievement. Somewhere beneath the flight deck, below the spaces where aircraft are armed and launched, in compartments that smell of industrial cleaner and cooking oil, and the particular olfactory signature of mass catering at scale, a culinary specialist is pulling a sheet of protein from a freezer that has been maintaining precise temperature for 62 days, logging it against an inventory count that has to be accurate to within tolerances that would satisfy a commercial auditor, and beginning a preparation process that will result in a meal consumed by someone who has been awake for 18 hours, performing a job where a mistake has consequences that extend far beyond a ruined dish. The ship that the public sees is the flight deck. The ship that keeps 5,000 people alive and functional is the one running silently underneath it. And the food distribution system is one of its most essential and least examined architectures. There is still one layer of this system that has not been examined here, one set of constraints that governs everything described above but operates on a logic that most people have never had reason to consider. And it concerns not the food itself but the humans who prepare it and the cognitive load they carry across a deployment that does not offer the recovery cycles that civilian food service workers take for granted, and what happens to the system's reliability when that human layer begins to strain under the weight of months at sea is a question that the Navy has studied carefully, and the answer it has arrived at says something precise and unsettling about the limits of any engineered system that ultimately depends on human performance sustained indefinitely under conditions no training can fully replicate.